All right, so last class we discussed the number system of binary and how we can get a number in binary and transform it into decimal. So let's very quickly review that, recap that. So if I want to convert a number from base 2, from binary into decimal, I need to add all of the powers of 2 in my binary digit where there is a 1. So here's all my powers of 2, 1, 2, 4, 8, 16, 32, 64, and 128 that are relevant to this digit. Let's add all of the places where there's a 1 together. So I have a 1 here, here, and here. 128 plus 64 plus 32 plus 1 is equal to 225. So this digit in binary equals 225 in decimal. Now, if I want to transform the other direction, if I want to get a number from from decimal into binary, first thing we need to do is find the largest power of 2 that will fit into the number that we have. So let's say I want to convert 100 from decimal into binary. If we look at our powers of 2, what is the largest power of 2 that fits into 100? Dean, I think you're muted, but yes, it's 64. So we have 64 is less than 100. 128, which is the next power of 2 up, is too big. So 64 is the largest power of 2 that fits into our number. So we're going to mark that as a 1 as the leftmost value in our binary number. So we're going to move right from there with all of the other powers of 2 we're looking at. If I want to continue, I'm going to subtract that power of 2 from my number, and then we'll repeat. So 100 minus 64 equals 36. So let's convert 36 from binary, or from decimal into binary. The largest power of 2 that fits into 36 is 32. So we mark a 1 in that position. Subtract 32 from 36, we get 4. If I want to convert 4, the largest power of 2 that fits into 4 is just 4. So we mark a 1 in that spot. 4 minus 4 is 0. And now that I have reached 0, I know that my conversion is complete. I can't subtract anything else from this without going into negative numbers. So I can fill in all of the empty spots in my number here with zeros. So I get 1, 1, 0, 0, 1, 0, 0. And that is the final result of our conversion. That's how we can convert a decimal number into binary. So with that knowledge in mind, let's discuss how computers actually store information. Like we talked about last class, all digital information, all of the information stored by computers is stored in binary. A single digit in a binary number, one of the things that is either 0 or 1, those are referred to as bits. And computers use only 1s and 0s because that is the easiest thing to read and to store. It's much easier to determine when you're getting an electrical signal if you are receiving a signal or if you're not receiving a signal, rather than trying to read exactly how much voltage that signal is carrying. What percentage of my maximum voltage is that signal carrying? Because I have to have a special sensor for that. I have to have all kinds of additional things, rather than just seeing, is this on, is this off? So that is the primary reason, is because it's the simplest way to do it. So if we look at the bottom of a CD really, 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 really closely, we can see that there are little raised areas, and then there's little and the rest of it is not raised. So we can kind of interpret those little bumps as either a 1 or a 0. So even physical media like CDs are using that 1 and 0 style of storing information. So we can read a bump as a 1, a valley as a 0, etc. So it's a little bit more complicated than that, but at a very base level, that is how CDs store information. So let's talk about how groups of bits, or how much different groups of bits can store. So 1 bit, like we said, is a single 1 or 0. That can only store true or false. That's not a huge amount of information. If I collect 8 of those together, 8 1s and 0s together is going to be called a byte. A byte is 8 1s or 0s, and that can store 1 character of text. So I can represent any letter on my keyboard using 1 byte of information. If I bring 2 to the 10 number of bytes, so a large number of these sequences, that is going to be 1 paragraph of text. So I can have about a paragraph of text in a kilobyte. A megabyte, that's the next step up. I'm going to have 2 to the 20 number of bytes. This is 1024 kilobytes. And about 3 megabytes is roughly how long a 3-minute song is in MP3, which is the most common compression format. And as we increase, we're going up by powers of 10 each time. And notice that we're using our metric system prefixes: kilo, mega, giga, tera, peta. As we go up higher and higher, we're using those larger and larger prefixes. So our devices are often going to have some number of gigabytes of storage. I know my phone has, I think, either 32 or 64 gigabytes of storage. Terabytes are 10 times bigger than gigabytes. Not 10 times, 1,000 times bigger than gigabytes. You can store all of the information in the Library of Congress in about 10 terabytes. I know my own personal computer, I'm pretty sure I have a 2 terabyte hard drive. So more and more information is becoming cheaper and cheaper to store in less and less space. As technology progresses, we're able to store increasing amounts of information in decreasingly large places. A petabyte is even bigger than a terabyte, obviously, the next step up. And I don't know why we're using Facebook photos specifically, but we can store 10 billion Facebook photos using a petabyte, which is just a huge number of photos. So let's look at individual bits and how many values we can store in them. So with 1 bit, like we said on the last slide, there's 2 possible values, 0 and 1. If I go up to 2 bits, there are 4 possible values: 0, 0, 0, 1, 1, 0, and 1, 1. That is every possible permutation of those 2 bits. If I go to 3 bits, I have 8 possible values: 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. Notice that as I am going up, I'm doubling in value, and that's because for each of my previous values, I can put either a 0 or a 1 in front. So I have 0, 0 with either a 0 or a 1. I have 0, 1 with either a 0 or a 1. And the same for all of the other values within my 4. So when I go from 3 bits to 4 bits, I can take all 8 of these, and I can add either a 0 in front or I can add a 1 in front to get 16 possible values. And as we add more and more bits, we're going to double the number of possible values each time. So when I have n bits, I have 2 to the n possible values, because that's how doubling works. So now if we have some sequence of binary, we're going to want to have some map of our things we want to store, like text. We want to store all of our values as a binary value. So if I use this encoding, let's say 0, 0 equals A, 0, 1 equals B, 1, 0 equals C, 1, 1 equals D. This works. I can encode a message. I could say 0, 0, 0, 0, 0, 0. That would be AAA. However, there are some problems with this encoding. First off, there are only 4 values I can represent here. That is not a huge amount of information that I can use to encode. So there's not many messages I could send that only take 4 characters, or for a sequence using 4 different characters. And secondly, only I know what this encoding is. So if I wrote a message in this encoding and sent it to someone, they might not know what it means, because if I don't send them this key, they won't be able to read it. So if everyone doesn't know the same encoding, then having this encoding isn't super useful. So let's look at Morse code. This was one of the first internationally accepted standards for encoding characters as symbols. So in Morse code, we are going to use dots and dashes to encode all of the letters of the alphabet and all of the digits. Notice that there are 2 symbols being used, a dot and a dash, in some sequence. So we can actually use binary to represent these characters using this encoding. A is going to equal 0, 1, B will equal 1, 0, 0, 0, C equals 1, 0, 1, 0, and so on and so forth. So we could use Morse code's encoding to encode all of the letters in the alphabet, all the uppercase letters, but that works, right? So Morse code was the standard for a long, long time. But as our digital data becomes increasingly complex, we're going to need to be able to encode more than just capital letters and digits. Turns out that we can encode all of the characters on our keyboard, all of the letters, both upper and lowercase, as well as all of our digits and a large number of symbols. We can encode all of those using just 1 byte, using 8 bits. And this standard is the ASCII table. We learned about this a little bit before, but ASCII, once again, stands for the American Standard Code for Information Interchange. So we are encoding all of our characters with some number. So the DEC, that is our decimal representation. We have a binary representation. We also have octal and hexadecimal, which are base 8 and base 16. So ASCII is the standard encoding for text used by computers all around the world. Every computer is going to understand that the number 1000001 represents the letter A, because this is the standard. So having this one encoding that all computers understand is super helpful, because we can have a message be encoded on one computer using this standard, and it can easily be decoded on a different computer because it follows the standard. So let's manually decode this binary sequence. If I have this sequence and I have my ASCII table, let's decode what it means. So I've taken a snip of the ASCII table containing just the letters, because since I encoded this, I know it's only letters. What is the first step going to be in decoding this sequence?
Would it be splitting it up into 7-letter segments?
Very, very correct, except I'm going to use a full byte. I'm going to use 8 character segments. So,
okay.
So we're going to 0, 1, or 1, 2, 3, 4, 5, 6, 7, 8. There's 1 byte. 1, 2, 3, 4, 5, 6, 7, 8. There's another byte, and we have a third byte. So we know that this sequence is going to be 3 characters long. So let's convert from binary to decimal now. So our first binary value is 0, 1, 0, 0, 1, 0, 0, 0. We have our sequence of our powers of 2. We can find all the places we have a 1, add those together. 64 plus 8 gives us 72. If we look at our ASCII table, 72 is the letter capital H. So our first character is capital H. All right, let's look at our next character. We have 0, 1, 1, 0, 0, 1, 0, 1. So we find all of our 1s, add those together. 64 plus 32 plus 4 plus 1, that gives us 101. We find that on our ASCII table. 101 is the letter E. So that's a lowercase e. Our last character is 0, 1, 1, 1, 0, 0, 1. If we add all of those values together, 64, 32, 16, 8, and 1, we're going to get 121, which, once again, we're going to look through our ASCII table. 121 is the ASCII value for Y. So our full message is, hey. Does that make sense how we can accomplish that? Cool. All right. So if in my programming, if in Python, I want to translate a character, I have a string with a character in it, and I want to find out what ASCII value it has, I can use the ORD function, ORD. I think it's short for ordinal, but I'm not really sure. So if I print ORD of lowercase a, I'm going to find a in my ASCII table and print that number. So I get 97. If I want to go the other direction and get the character based on its ASCII value, we can use the CHR function. So if I print CHR of 65, it's going to reference where it's 65. Oh, that's the letter capital A. So if I wanted to use these to translate from binary to text or vice versa, let's say I wanted to write the code to accomplish this, that idea. So I've written this function, our binary to text function. We're going to get a binary sequence as a parameter. We're going to create a string to store our translated text. We're going to loop starting at index 0, going up until the length of our binary sequence. And we're going to increase our iterator by 8 each time. So we're going to move 1 byte at a time through our binary sequence, which we're assuming is going to come through as a string. Our current byte is going to equal the slice in our binary sequence starting at index I and ending at index I plus 8. So we're going to grab an 8-character slice out of this string, and we can slice strings just like we can slice lists and tuples. So we grab our current byte. We're going to call the bin to deck function. I wrote this, so you'll need to have your own way to turn a binary number into a decimal number, but I'm going to call my function to turn that byte into a decimal number, save that in my variable ASCII value. I can call my CHR function, my character function, on that ASCII value to find out what that character is, and then I can add that character to my translated text. And then when I've looked at all of my bytes, I can return my translated text. So does that code make sense, how we can accomplish translation? Sweet. All right, folks.